All right. So this work is about dynamic resource management with MPI sessions and pmIx. And to give you some context about this work, dynamic resources is one of the main topics which are currently discussed in the MPI sessions working group. And the main intention of this work was to provide some concrete reference points to be used in this ongoing discussion. So I will start this presentation by introducing the main ideas of dynamic resource management, the MPI sessions model, and the pmIx standard. With dynamic resource management, you can change the resource assignments of jobs dynamically during the runtime. And this is contrary to the state-of-the-art batch systems, which usually use static resource assignments. So the resource assignments of jobs cannot be changed during the runtime. And dynamic resource management can have many benefits. For instance, it can improve the resource utilization from the global systems perspective. For instance, it can improve energy efficiency or job throughput, but it can also improve resource utilization from the individual applications point of view, and especially for those with dynamically varying resource requirements. And moreover, dynamic resource management can improve data locality, and it can also help to support urgent computing and fault tolerance schemes. So a very active research area revolves around the question how to enable such dynamic resource management on HPC systems in the right way. And this is quite a complex question, as dynamic resources require support from various components in the system software stack. So on the one hand, we of course need dynamic scheduling algorithms and a dynamic resource manager, but also the applications itself have to be able to cope with adding or removing resources such as compute nodes during the execution. And for this, we also the programming models used by these applications have to provide such dynamic capabilities. And in this work, we in particular target the MPI programming model. And our main contributions here are the definition of a dynamic MPI interface based on the MPI sessions model. And we also explain how this interface can be implemented on the runtime level using the pmIx standard. So the process management interface for exascale, pmIx, can be used on many different parts of the HPC software stack. But in this overview, I will restrict myself to the parts which are particularly relevant to MPI implementations. So in MPI implementations, the pmIx standard is usually used for bootstrapping MPI processes and to provide MPI runtime services. And there are two main pmIx abstractions which are important in this context, the pmIx server and the pmIx client. And usually each MPI runtime daemon operates a pmIx server on its local node. So before starting the MPI job, it first registers the job information at its local pmIx server using this pmIx server register nspace function. And after that, the MPI processes can connect as pmIx clients to the pmIx server at the local node during the MPI initialization step. And this gives the MPI process access to the pmIx services which are defined in the pmIx client interface. And this includes, for instance, access to a distributed key value store, where also the job information is stored, but also process synchronization and an event notification system, to just name a few. And it's important to keep in mind that pmIx is a messenger and not a duo. So most of these services actually require action by the MPI runtime itself. And for this, the pmIx standard provides function definitions to pass on the requests from the pmIx server to the MPI runtime. And the MPI runtime has to provide the implementations of these functions to support these services. So when introducing a new dynamic MPI interface, it's important to keep these pmIx aspects in mind, as most MPI implementations rely on the pmIx standard for the runtime environment. So our approach for dynamic MPI is based on the MPI sessions model, which is a new MPI model introduced in the 4th version of the MPI standard. And it mainly avoids the creation of a global MPI world communicator during the MPI initialization, which often was a major limitation of dynamic MPI approaches, which were based on the world model due to global synchronization requirements. So instead, in the MPI sessions model, the MPI communicators are derived from so-called process sets, which are unordered sets of processes, and they are labeled with unique identifiers in the URI format. So here you can see an example how the runtime environment could associate processes with process sets. And there are two process sets which are mandated by the MPI standard, the MPI world process set and the MPI self process set. And these process sets mainly contain the processes which would be associated with the world and self communicator in the world model. Now, to create a communicator from such a process set, a process can first query the runtime environment for information about available process sets, and can then use the name of such a process set to create an MPI group. And finally, from this MPI group, it then can create an MPI communicator. And now our approach builds on top of this MPI sessions interface. And our main goal for this dynamic interface was to provide a very general approach to make it applicable to a large range of different application use cases. And to approach this goal, we used a set and graph-based abstraction, which extends the set abstraction, which is already at the core of the sessions model. So for our abstraction, we use 4 core assumptions. First of all, there can be unordered, possibly overlapping sets of resources, where the process sets of the sessions model are one example. Then second, there can be set operations, such as union, difference, or intersection, be executed on such sets to create new sets. So this could represent resource reassignment of the resources inside of an application. Now, taking a graph perspective, we can represent the resource assignments of an application with a graph, where the vertices of the graph are the sets, the resource sets, and the directed hyperedges of the graph are the set operations. And now, following this graph perspective, resource changes can be associated with particular vertices in this graph. Or in other words, it can be associated with particular resource sets of an application. And this allows us to target really particular parts of an application with resource changes. So the information about resource changes consists of 2 parts. The type of the resource change, which could be, for instance, addition or removal of resources. And second, the name of the so-called delta set, which is a resource set which contains exactly the delta between the resources before the resource change and after the resource change. So for resource addition, it would contain exactly the resources which are added to the application. Now, based on this abstraction, we created the following possible dynamic MPI sessions interface. However, it should be kept in mind that this is just a proof of concept, so it is very likely that the details of this interface will change based on the ongoing discussion in the sessions working group. And also here, for the sake of brevity, I will only show the blocking signatures of these procedures, but we also implemented non-blocking variants, which can be quite useful in many application use cases. So the first new procedure we introduced allows an MPI process to query the MPI runtime about resource change information. And here we follow the abstraction. So the resource change information is always associated with particular process sets. And so the input parameter to this procedure is the name of the process set for which the resource change information should be queried. And the output parameters then are the type of the resource change and the name of the delta process set. So for the type of the resource change, we have currently 3 constants. The MPI RC none constant indicates that there is no resource change information associated with the process set. And MPI RC add and sub refer to addition or removal of processes respectively. And for convenience here, this procedure also returns a flag to indicate that the calling process is included in the delta process set. And one specific MPI detail here is that we assume that resource changes are always associated with the MPI self process set if this process is included in the delta process set. Then the second new procedure allows an MPI process to request process set operations from the MPI runtime. And this allows an application to reassign applications resources according to the specific needs of an application. So to give you one example, a typical operation which could be executed as a response to adding processes would be the union operation between the associated process set and the delta process set to create a new union process set, which now also contains the dynamically added processes. So the signature of this new procedure is relatively straightforward. The first input parameter is the set operation which is requested, and currently we have 3 constants referring to the union, difference, and intersection operation. And the other 2 input parameters are the process set names, which are the arguments to the set operation. Then the output parameter is the name of the resulting process set. And then the last new MPI procedure is not directly derived from the abstraction, but it is useful as it can help applications to integrate such a resource change into the workflow. And to this end, this procedure provides a rendezvous and synchronization mechanism between the associated process set and the delta process set, and is collective over the union of these sets. So to give you some motivation for this rendezvous mechanism, let's take the example from the last slide, where the application has created a union process set. And now a logical next step for the application would be to create a communicator from this process set. However, in general, the dynamically added processes do not necessarily know which process set name they have to use to create this common communicator. And for this new procedure provides a publish lookup mechanism to make a process set name available to the processes in the collective. So the 3 main parameters of this procedure are first the name of the delta process set, which refers to the resource change which should be integrated. And second, a flag, which indicates that this process is the single one process that provides the process set name that should be published. And third, a buffer for the process set name, which is similar to an MPI to a buffer in an MPI broadcast function. One detail here is that if a process is not the one which provides the process set name, it can also provide a null pointer as buffer to avoid the lookup operation. And for convenience, this function also returns a flag to indicate that the process is expected to terminate, which could, for instance, be the case when removing processes. So it should be noted that for this procedure, it is particularly useful to use a non-blocking variant, as this allows an application to progress with its workload while it waits for the dynamically added processes to reach the collective. Now, to illustrate the usage of this interface, I will show a small example. And in this simple application, only one communicator is used, which would be the world communicator in the world model. Or in this case, we derive this communicator from the MPI world process set. And then this communicator is used in a main loop for an application-dependent iterative workload. Now, to make this application valuable, we have to adjust the initial creation of the communicator, and we add a resource change step at the end of this main loop. So to create the initial communicator, a process first queries the runtime environment about resource change information associated with the MPI self process set to check if this process is a dynamically added process. And if this is the case, then the process calls into the integrate rest change procedure to receive the name of the process set to be used for the initial communicator and to synchronize with the already running processes. Now, on the other side, in the main loop, in the resource change step, there is one process responsible for querying the runtime environment about resource change information associated with the currently used main process set. And if there is such a resource change, then it executes set operations according to the needs of the application. So in this example, it creates a union process set from the main process set and the data process set. And after that, it broadcasts the queried name of the data process set to the other processes in the loop. So they can all use this name to call the integrate rest change procedure. And in this procedure, then the name of the new process set is transmitted to the dynamically added processes, and the synchronization happens. And after that, all the processes can use the same process set name to create a common communicator. Then in the next iteration, they can use this communicator now with the additional processes. So this was the MPI part of the new interface, and now I will go on to the pmIx part. And in this part, I will describe how the pmIx standard can be used and extended to support the implementation of this MPI interface. So in the following slides, the red text indicates extensions to the pmIx standard, and the blue text refers to the parameters of the MPI procedures. So for the first new MPI procedure, we can rely on the already existing pmIx query info function, which allows a process to query a system and runtime information. And now we have to specify a pmIx query for resource change information. And for this, we introduced two new pmIx query keys, one for the data process set and one for the type of the resource change. And we also introduced a new key for the associated process set, which we use for query qualifier to restrict the query to this process set. And then the result is passed as key value pairs using also the new query keys. And for the type of the resource change, we also introduced three new pmIx constants, which are similar to the MPI constants. And for the set operations, we introduced a new pmIx service, as there's currently no functionality in the pmIx standard that allows processes to create new process sets. So here the client interface of this procedure is basically a straightforward translation of the MPI procedure into pmIx terminology. So we also use constants for the union difference and intersection operation to specify which set operation is requested. And then we pass the names, or the names of the process sets are passed as key value pairs using new pmIx keys. Now this request is then sent to a local pmIx server, which forwards the request to the MPI runtime using a new function definition we introduced. And the MPI runtime has to provide an implementation of this function to support the service. And this implementation is expected to execute the set operation and to define the new process set before it calls back into the pmIx server using a new callback function we introduced. And then the results of this operation are passed down to the pmIx client. And then for the integrate rest change procedure, we can fully rely on already existing pmIx functionalities. So for the publish lookup mechanism, we can use the pmIx publish lookup interface. So the one process which provides the process set name publishes it with a well-defined unique key for the resource change. And this way, the other processes in the collective can use the pmIx lookup function to look up the process set name. Then the synchronization is achieved with the pmIx fence function, which executes a barrier across the specified processes. And after that, the one process which published the process set name again unpublishes it with the pmIx unpublish function to avoid an accumulation of published data in the data server. So we implemented our first prototype of this approach, and this prototype is based on OpenMPI, OpenPmIx, and PRT, the pmIx reference runtime environment, which is the runtime environment used by OpenMPI. And here I don't want to go into all the details of this figure, but I want to briefly touch on how resource changes are triggered in this prototype. So resource changes are triggered by sending a specific pmIx event notification code to the PRT master process, which is the process that executes the PRT run command and which also starts the PRT daemons on all the compute nodes. And this PRT master process has registered a callback function for this event code. And this callback function according data process set for the resource change is defined, and some updated job and query data is then sent to the 30 daemons, which update the local data and possibly start new processes in the case of process addition. So to evaluate the usability of this approach and to provide some preliminary performance results, we have run some tests on the LRZ Linux cluster. And for this, we used a Slurm allocation of 4 nodes in a total of 112 cores. And our test applications were run inside of these allocation bounds, and the number of processes were changed dynamically. So our 2 test applications are a synthetic benchmark, which is pretty similar to the code example I showed before. And the other application is a PDE solver, which uses the pForest library for adaptive mesh refinement and load balancing. So in the table below, the highlighted row shows the application overhead related to resource changes, including the creation of the new communicator for addition and removal of processes. So for adding processes, the overheads are between 100 and 200 milliseconds. And for removing processes, around 100 milliseconds. And these overheads slightly increase with an increasing number of added and removed processes. But in comparison to the time required for the workload, these overheads are moderate. If you consider the graph on the right side, which shows the time required for the workload in each iteration as the black bars, and the overhead related to the resource change as blue bars, we can see that that the blue bars are relatively moderate compared to the black bars. So then our second application was a PDE solver, which uses the pForest library for adaptive mesh refinement and load balancing. And for our tests, we simulated a radial dam break scenario, which you can see here, by solving the shallow water equations. And we used our prototype to add or remove processes dynamically during the execution of the application. And again, here the black bars is the time required for the workload in each phase of the solver, and the blue bars are the overhead of the resource change related to the MPI part. And some additional overhead here arises from the pForest internal processing of the resource change. So this includes, for instance, the repartitioning of the grid and the data rebalancing. But overall, you can see that by adding processes dynamically, we can reduce the time required for each phase. And the overheads are comparably moderate if you compare it with the time required for the workload. So overall, these are some first steps towards dynamic MPI based on the MPI sessions model. But dynamic MPI is also only one step towards our main research goal, which is to provide operational malleability on the whole HPC system. And for this, we think that our set and graph-based view on resources might be an important building block, which could also be used independent from MPI. But this research requires a collaboration across the full HPC stack. So this includes different application use cases, MPI implementations, the pmIx standard, and also schedulers and resource managers. So there are currently 4 EuroHPC projects working on malleability, and there's a large interest for collaborations in this community to really bring forward the research on really providing operational malleability on HPC systems. So this brings me to the end of my presentation, and thank you very much for your attention.
Is there a way to time out on resource requests? So if I ask you for, I don't know, 128 more nodes, but you can't give me the nodes, and I don't want to wait for 2 hours, what do I do?
Yeah, currently in this work, we haven't implemented the requests of resources. So this is the next step to really allow an application to request resources. So in this case, you were you had a guarantee that you get the resources you request. But in the next step, we want to combine our prototype with malleable prototypes of resource managers such as Slurm. And then we want to implement the interaction between the scheduler and the MPI implementation too. And there we will have to think about such issues.